Okay, guys. Next video that we're going to do in 5500 and 6500. Hate it when I write and it doesn't show up. And what we're going to do now is we're going to investigate what we call a two-sample t-test. Now, what you need to think about here is we have some population. And this population, we'll just call this population 1. And this population has a mean, so we'll call that mu sub 1. And it has a variance, which we'll call sigma squared sub 1. And then we have another population. We'll call this population 2. So it has a mean, we'll call mu sub 2. And it has a variance that we'll call sigma squared sub 2. Now, what we would like to investigate is we would like to compare the means from the two populations. So ultimately, we're wanting to know here, how do these two compare? And more specifically, is the mean from population 1 equal to the mean from population 2? Now, the way these things usually work, or at least that they work a lot, is you have one bigger population that you divide into two groups. So an example of something that we may do here, if we were looking at, for example, ACT scores, we may want to divide this into public schools versus private schools, and see if there's a difference in mean ACT scores across, across public and private schools. Now, what we would do here from population 1, with mean 1, variance 1, we would collect a sample. And what we would do here is we would collect a sample mean of size n1, and of course we would have a sample variance. Let's put a 1 right here just so we're clear. We would have a sample variance from this population. So from the first population, which I said, I think, what, public schools? Yeah. We would go in, collect decide on a sample size, get a sample mean, and calculate the variance. Now, from the other population, again with mu sub 2, unknown population mean, and variance, well, we do the same thing. We would, from sample size n2, we would calculate a mean, and we would also be able to calculate the variance from this population. Now, the goal is pretty clear once you set up the null and alternative hypothesis. The null hypothesis, again, kind of the lazy one, is there's no reason to do this test. The population means are equal. The alternative hypothesis, more aggressive. So, I don't know about that. I think we need to do some testing to check that whether they're equal, because they may not be equal. Now, the biggest hurdle for my students at the undergraduate level, and I don't think it's going to matter really undergrad or grad, is to see that you're, at the end of the day, really not testing to see if the means are the same. What you are really testing is whether or not the difference of the means is equal to 0, or whether or not the difference of the means is not equal to 0. Now, guys, obviously this statement and this statement are equivalent. This statement and this statement are equivalent. But this notation, this thought process, makes things a lot simpler when we start investigating our confidence intervals, because our confidence intervals are going to contain the difference of the means. So if we go ahead and kind of set the thought process initially that we're examining the difference of means, again, it's going to make the confidence intervals, at least the interpretation of the confidence intervals, make more sense. Now, gang, you would, you know, regardless of your statistics background, if you're going to investigate the difference of two population means, it should make a lot of sense to you that the point estimate that we would use would be the difference in the sample means. So in terms of our underlying probability distribution, this is going to serve as the point estimate of the value that we're going ultimately try to estimate. But what's the variance going to look like? Any distribution, we're typically worried about, or at least concerned or interested in, what's the center and what's the spread. Now, for example, in a normal distribution, if I tell you the normal distribution is centered at 100, well, that only tells you half the story. To get the full information on the probability distribution, you also need to know what the standard deviation is. Well, there's a well-known fact in probability that the variance of A minus B is equal to the variance of A plus the variance of B. Well, this leads into something kind of cool for us, because we would like to know what the variance of x bar 1 minus x bar 2 looks like. And it's pretty simple from what I just gave you. So it's going to be the variance of x bar 1 plus the variance of x bar 2. Now, if we think about, we typically want you know, our underlying probability distributions to be expressed in terms of the standard deviation. So we very easily can see that the standard deviation, therefore, of x bar 1 minus x bar 2 is just going to be the square root of the variance. All right, and the variance for x bar 1 and x bar 2, and we should know this from central limit theorem. And if you're sitting there thinking, well, I don't know this, don't sweat it. I'll teach it to you. Is this, and we can, let's see what I want to do with this. We can make this a little cooler. Yeah, let's do this. And let me come back in and put the subscripts of the N1 and N2. Okay? Now, typically sigma 1 and the variance of the populations are unknown. Not always, but typically they are. So obvious measurement to use to estimate the variance of population 1 would just be the sample variance, and similarly speaking, the sample variance from population number 2. So guys, at the end of the day, we know that the standard deviation of the distribution of the difference of means, did I really say beans? I meant to say means. Alright, is S1 squared over N1 plus S2 squared over N2. So, gang, we now know where our distribution is going to be centered. It's going to be centered at x bar 1 minus x bar 2. We now know what the standard deviation is going to look like. It's going to look like this stuff. Now, what does the distribution look like? Well, some people say, well, it'll be the z distribution. Well, no, because this is just extremely annoying when I get out here to the end and I can't write. No. Well, pretend there's a pretend there's a question mark after distribution because for some. Hey, here you go. There you go. So, what is the distribution? Well, some people say the z distribution, and that's not the case because the population standard deviations aren't given. So the next guess is the t distribution, and the answer to that is, well, sorta. It's a lot of people don't even realize this, and they violate things. But the t distribution comes really close to modeling this phenomena, but it needs a little bit of correction. And guys, unfortunately, the correction for this is extremely crazy. So remember, the t distribution is always a function of its degrees of freedom. And in this situation, the degrees of freedom turn out to be extremely ugly to find. It's really not that bad, but actually it is pretty ugly, isn't it? So it's this nasty mess. Now, this brings us into a very interesting situation. And what I've done here is I've set up the framework for what we call an unpooled two-sample t-test. So let's talk about a pooled versus unpooled two-sample t-test. And what should you do? Well, guys, after this video, I'm going to post a link to a YouTube video that I use quite often. The guy did an awesome job. He came in and violated the assumptions of the equal variance, and of course, violating the independence assumption is always going to cause your p-values to be unstable. But he came in and looked at what happens when we violate the equal variance assumptions, and he did a really good job. Did simulations and shows the reason that we make the decisions we do in terms of choosing unpooled or pooled. Guys, a pooled two-sample t-test makes the assumptions that the population variances or population standard deviations are equal. An unpooled t-test does not make this assumption. Now, in this video, I'm going to show you how to construct both. And everything that I did previously in terms of the standard error, the standard deviation of the distribution of the mean differences, and the degrees of freedom, these are all unpooled. Now, if we can make the assumption that we have equal variances, there's this clever way that we can kind of put the standard deviations together and come up with what's called a pooled within variance. And I'll illustrate that as well. So, guys, right now, everything that we're doing focuses on the unpooled technique. which doesn't assume that we have equal variances. And again, gang, you know, I'm going to post again a YouTube video link after that addresses this situation nicely. So, guys, right now we are going, I am going to demonstrate the unpooled two-sample t-test. And you've probably seen this before, but you know, if not, welcome, I guess. All right, gang, let's do this. I want to get out of this, and I'm going to need R, and I've already got it up. And let me show you too on my desktop, right, or I hope I do. Yeah, right here. You can see that I have the IQ read file that I talked about, I think, in video number 1 or number 2. I already have it on my desktop. Okay, so I'm going to go get that, and I'm going to use that to demonstrate the unpooled and pooled two-sample tests. Okay, so first thing I'd need to do is set my working directory, and I never really remember what the form is, so I just get it and then use the form to set it. So I want to set my working directory as users ddarbro desktop. Okay, now I've told R where I want it to look for files. So I'm going to get my data using the read.csv, and I will tell you there is a read.xls command in R. I find the CSV to be much more stable and consistent. The read.xls I get to work about half the time. The read.csv I get to work every single time. Okay? Now, you know, no error, no red warnings pop up, so that's good. Next thing I need to do is come in and attach my data. I'm not going to be able to do any analysis with my data until I attach it. And you know what? Most people, especially at first, they like to type data and they like to see what they've done. So I never do this. I know it's there once I attach it. And, yeah, whatever. It's up to you. All right, gang. Here's what I want to do. First, I want to demonstrate the unpooled two-sample t-test. And remember, if I start something with a hashtag, that's the way I can communicate to you. And oftentimes, when you do an assignment where I ask you to do stuff in R, you're going to communicate to me things that you've done. So remember, start with the hashtag. Okay. Now, the first thing I'd want to do, and my goal here, is I want to examine the mean difference in read across gender. Okay? So at the end of the day, I'm not really too concerned with LSS, IQ, estimated reading level, and school district, just these two. So now if I go mean of read, what I'm going to do is I'm going to get the mean for everyone combined, but I don't want that. I need the means for each male and female. So it's kind of weird the way you do this. Actually, there's multiple ways to do it, but the way that works really kind of cool. Well, I don't know if it works cool. It just works. All right. Is something called t-apply. And what I can do here is I can go read, let me think this through. I'm not sure I'm right on this. Let's see. This is not going to work. Let me think. Okay, don't write this down, guys. Yeah, this ain't going to work. Now, here's what we got to do. This is one of the weird cases where you use, yeah, okay, this is going to work. Okay, guys, the format for t-apply, so many times when we have a quantitative data over a category, we use this notation. but this one isn't like that. So it's just your quantitative data, comma, your categorical data. And then this fun, it doesn't mean that we're having fun, well, maybe it does. It's just function, and we want to find the mean across gender. Okay? Now, I'd also need to find the standard deviation. And remember, in R, standard deviation is SD. So you probably want to write this down, the means, and I'll tell you what, let me go ahead and get this established. Something else we're going to want to do is I want to do t-apply, and I want to get the sample size of each. And I hope you remember that sample size is a length. So we have 12 females and 18 males. So guys, I'm going to go over to my blackboard, and I'm going to write this stuff down. So it looks like we have X bar for males is 60.72. The standard deviation for males is 21.085. And the sample size for males is 18. So sample mean for females is 57.917. I'll tell you what, let's just go 57.92. The standard deviation for females is 27.232. And the sample size for female is equal to 12. All right, so let's go back over to okay, I've lost my connection here. I don't know what's going on here. It's not cool. There we go. All right, good deal. Now, my computer's gone wacky on me for some reason. Okay, so we've got the descriptive statistics across the two groups. Okay, so first thing we're going to want to do is set up our test. And again, what we're going to do here is we're going to test that the mean difference for males minus the mean difference for females is equal to 0. And I'm just going to construct a two-tailed test. The mean difference for males is not equal to 0. And guys, let me show you a little trick. You know, at this level, negative numbers are not a major ordeal. But what I like to do is I like to keep my difference positive. So after I run the descriptive statistics, I see that the sample mean for males is bigger than the sample mean for females. This keeps the difference positive. It's not a major deal, but I think it makes it just a little bit easier to interpret things once we get, especially to the confidence intervals. You don't have to do that, but it's just a little trick that I do. Now let's talk about the descriptive statistics and some things that you need to start thinking. Up to now we see things like this. Okay, we just write it down and go for it. But guys, you need to start thinking a little more critically, I guess. The stakes are a little bit higher once you get to this level. Now, the first thing we look at is obviously the male mean is about 3 points higher than the female mean. The dumbest, absolute dumbest thing you can do is conclude, well, males have a higher reading score than females. That's not true. These 18 males have a higher average reading score than these 12 females. But when we conduct inference, we are generalizing to a bigger population of all males and all females in this age group. So the sample mean doesn't tell us, the sample mean difference doesn't tell us anything more than there's a difference between these 18 kids, these 18 males, and these 12 females. Let the process play its way out using the underlying probability distribution, standard errors, degrees of freedom. Let everything play its way out. The next thing that's kind of tempting, kind of not, is to examine the standard deviations. We're always on guard here, or always at least looking to see if there's evidence that the population standard deviations are equal. Well, the sample standard deviations certainly aren't equal. And to me, 21 versus 27 is a pretty significant difference in terms of us sort of generalizing, or at least thinking that the population standard deviations are equal, or population variances. I still don't know. Again, sample standard deviations vary from sample to sample. So these things aren't concrete. If I went in and took another 18 kids, this would be different. If I went in and took another 12 kids, female, that would be different. There's natural sampling variation in our means. There's natural sampling variation in our standard deviations. But nevertheless, based on this one particular sample, this is too much difference for me to really feel comfortable concluding that the population standard deviations are equal. So I feel extremely comfortable, and I'll kind of give you the punchline here in a minute. I feel extremely comfortable in this situation constructing the unpooled t-test. So guys, we got this. I don't see any reason not to test at alpha equal 0.05. Now, hopefully after the errors and type 1, type 2 video, you understand a little bit more about that. All right, gang, the next thing we need to do is we need to calculate the test statistic. And the test statistic is x bar 1. Well, let's be consistent here. For females divided by the standard error for the difference in the means. Okay? So let me see. I wrote down the means someplace because I knew this was going to happen. Okay, so let's go to the next screen where I've got room to write. So the mean for male was 60.72. Mean for female, 57.92. And this is over the square root of 21.085 squared over, what, 18? Yeah. And 27.231 over 12. All right, boys and girls, let's see if we can get that in our calculator without doing something insane. All right, I need to be talking or something. This silence is driving me crazy. Don't know really what to talk about, but does anyone get 0.301? All right, because of the importance of this, I'm going to double check my work. I hate doing a video where I actually get into calculations and find out that make sure I got no typos. All right, gang, everything looks good. So what would we say here? We would say that, given the null hypothesis, or at least under the conditions of the null hypothesis, that the mean difference is equal to 0, this sample mean difference is 0.301 standard errors above the mean. Okay? Next thing we need to do is calculate the p-value. Well, guys, the p-value, the underlying probability distribution, since we're constructing a two-tailed test, going to put half of our rejection region in each tail of 0.025. Now comes the fun part. We are dealing with the t-distribution degrees of freedom equal that total big nasty crazy mess. And I'm just going to write mess there because it is really messy. But guys, nevertheless, we need to find that. So let's go for it. So our degrees of freedom for this crazy problem, and this is the worst part of it, will be 21.085 over 18. Plus 27.231. Over 12, quantity squared. And then we have, what, 1 over 11? No, we don't. Thinking ahead here. Now 1 over 17 times 21. Over 11. Well, that's the ugliest 2 in the history of 2s. All right, let's have fun with this, guys. So go to the next page. Wow, this is going to be horrible. Alright, actually, guys, what we should get is we should have 7,480.9839 in the numerator, 35.884 plus 347.1356, which gives us 19.532. So guys, what are you going to think about here? This is your degrees of freedom. So the underlying probability distribution that that models this, the distribution of means for this situation has degrees of freedom 19.532. So back to here, we can get rid of mess. And we know that 19.532. I have no earthly idea why when I get to this spot right here, I have a hard time writing. Alright gang, we need to go to R and calculate the p-value. Does anybody remember how to do that? Wish you could answer me, but you can't. All right, well, I'm going to show you how. So let's go to R. And we got to remember we're doing a two-tail test, so we're going to take 2 times. Got to account for both tails. And I'm going to use PT. And I want the area below. Now, this is a situation where you can use a little kind of, I'll tell you what I need to do. Let me, I need to explain this. This is always a source of confusion. Because my computer is running incredibly slow. So what we have is in the sampling distribution with the degrees of freedom 19.532, the test statistic that we came out with way back when was like 0.301 right there. So we need the area from 0.301 up and from negative 0.301 down. Now, the function PT and R gives us area below a particular value. If I just put PT 0.301, it's going to give me this area. Now, granted, I can come in and subtract by 1. But guys, in this situation, it's going to be easier for us to find this area right here, multiply by 2 to account for this up here. I hope that's clear. So